Alright, so today we're going to talk about scientific measurements. We're going to look at the difference between accuracy and precision. We'll figure out how to determine the number of sig figs, I call them, significant figures in a measurement. We'll do some mathematical operations involving sig figs. And if we get far enough today, we'll talk some about scientific notation, but that might be for the next lesson. So first off, I just want to define these two words, accuracy and precision. They both kind of sound similar, but there's a little bit of a difference between them. Accuracy tells me how close my measurements are to the correct value, and precision tells me how close my measurements are to each other. So let's just say, for argument's sake, when we measured the sponge to see how much water the sponge can hold, let's just say that it was supposed to hold 5 times its weight. So you do the lab and you measure it and you get 5.2 times its weight when it's supposed to be 5. I'd say that this is pretty accurate, right? But not to mention any names, but if you had a sponge that maybe held 10 or more times its weight, then that's probably not quite as accurate, right? So accurate literally just tells me how close to the expected value I should be. Precision, on the other hand, tells me how close my measurements are. So let's say I did the lab 3 times and I got 4.1, 4.1, and maybe 4.2. Those 3 measurements are all really close to each other. Maybe not quite the most accurate measurements, but I'm doing something consistent. So I'm getting the same result over and over again. That's what I mean when I say precise. How close are my measurements to one another? And it might be easy to see with a set of darts to kind of visualize accuracy versus precision. If I throw darts at a dartboard and I get them all right on the bullseye, right on target within that circle, that's high accuracy, and I'm doing it over and over again, so I'm doing it with high accuracy and high precision. If I'm getting them in the same spot down here in the bottom left, I always hit that spot, that's my spot, but I can't get the bullseye. I'm being very precise, but there's something off about my throw that every time I throw it, it's not quite getting the bullseye. So this B here would be an example of something that's very precise, but not accurate. So in the lab, that might mean I have a systematic error with my scale. It's not calibrated. Something is causing me to, I'm consistent with it, but it's causing me to always be off a certain amount. On the right there, we have something that's very low accuracy. You're not hitting the bullseye at all. And it's also very low precision because I'm all over the place on the dartboard. I do want to talk about one other case because I think it happens enough to mention. We could have a condition where I have good accuracy but low precision. Like let's say I hit the dart like one directly above and one about the same distance directly below and one over here to the left, one over here to the right. If I hit those 4 places, it would average out to be the right answer, like right in the bullseye. But I was not precise at all. I kind of just lucked into averaging the bullseye. I'm not very good at darts just because I got the average being the bullseye. Same with in the lab, like if I was trying to get 5 with the sponge. I got maybe 1 and 9, which would average to 5, but that sounds like terrible lab technique if you get 1 the first time and then 9 the second time. You're all over the place. So hopefully that makes sense, the difference between accuracy and precision. So let's go ahead and talk about this one. Just to make sure we're awake, it should be an easy one. The accuracy of a measurement, what's my answer there? And then this one is going to be in the lab. We have the mass of a product was supposed to yield 8.60 grams, and then I got 8.93 for the first trial, 8.94 for the second, and then 8.92 for the third. Does that make sense between? Yeah. So this one is coming up in our mixture separation lab. We have the percent error. Some of us are calculating that. I think we're still working on the physical and chemical changes stuff. So not necessarily there yet, but we will be. And when we calculate the percent error, we're going to take the accepted value, subtract it from the experimental value, and then divide the difference. So my equation would look like this. I have the value I obtained. So what you guys are doing is you're going to measure out the sand, the salt, and the iron. So you know how much you measured. When you separate them back out, your accepted value should be what you measured out to begin with, and then your experimental value is going to be what you end up after you separate the mixture. And then you're going to take that divided by the accepted value. It should be a small number, less than 1, unless your experiment is really off. But it should be a small number, and we're going to multiply that by 100 to turn it into a percent. So let's try that with an example. The student measures the mass and volume of a substance, finds its density to be 1.40. The correct value is 1.30. So what's the percentage error? First off, can you tell me which one is my which one's my experimental value? Yeah, I'd say the 1.40, what the student measures, and then my accepted value, they tell me, is 1.30. So the way I set it up is I take my accepted value, subtract the difference between that and my experimental value, and then the one I divide it by is always the experimental. Or, I'm sorry, it's always the actual. I'm sorry. So I'm going to take it divided by 1.30. So I take 1.40 minus 1.30 is going to give me a difference of 0.10. Yeah, 0.10. And then, so I still have to divide it by 1.30. So 0.10 divided by 1.30. I guess I already did it in the last class. It's up there for you, but it's 0.0769. And remember, I have to multiply that by 100 to put it in percentage form. So I get 7.69%. And that is my percent error. So do you have any questions about that? Makes sense how we did that? All right. So why do we do the percent error? It's because there's no experiment you can do that doesn't involve some kind of error. I don't know if you've had this problem, but I know some people have been looking at the scale. The last number on the scale kind of goes wild all over the place. So you have to just come up with something. It's like 4 1 second and an 8 the next second, that last number. So on the scales, they're not always, completely even, so you have to take a guess a little bit. So that could be the measuring instrument. It could be the skill of the measurer. Maybe you're just kind of not exactly measuring something exactly where you should measure it, and you're a little bit off. Or the conditions you're under could have an effect. So these are all things that when you're doing your lab reports, you want to make sure you're aware of when you're talking about sources of error in your analysis. There could also be, like, if we're dealing with chemicals, if the chemical is not very pure to start with, and then you're assuming it is, it's going to affect your calculations down the road. So we want to talk about significant figures because it's important to know how precise our measurements are. So significant figures are all the digits that we know in a measurement plus one that's estimated or uncertain. So going back to the scale, if I see that it's 2.38 1 second and 2.34 the next second, I know it's 2.3 something. I just don't know what that last digit is, so I have to make my best guess. We can see that with a ruler pretty easily. If you look at this nail, we all agree that the nail point, if this is 6.123, we can all agree that that nail point is somewhere between 6.3 and 6.4, but it's the third number that we're not 100% sure about. So with 6.3 and 6.4, for me, I think it's about splitting in between. I even think it maybe a little bit to the right, or your partner might think that. So one of us might say 6.35, some of us might say 6.36. So either way, we know it's 6.3 something, but that last digit is uncertain. Here's the thing, though. It's still significant. Just because that last digit is not certain doesn't mean it's not significant. Because significant figures have to have all the measurements used plus one more digit. So here's where we get into the rules for Sig Figs. Most of them are pretty straightforward. It's really when we get to the fourth rule that the confusion comes. But I want to talk about, to me there's actually 5 rules. There's kind of an unspoken rule up here. It's the most obvious one, is that all non-zeros are significant. So everything that's not a zero counts as a sig fig. It's really the zeros that cause the problems. So the first one is pretty straightforward. The first one says zeros appearing between non-zero digits are significant. So like this 0 and the 40.7 and these 2 zeros and the 87,009. They are all significant because they're sandwiched between non-zeros. So as long as you're sandwiched between non-zeros, you're fine. You kind of join the crowd and become a significant figure. However, on the other hand, these numbers before the first non-zero are not significant. So all those zeros don't count as significant. They're needed. I need them there to tell me I have 0.009 kilograms, a small number of kilograms, rather than 9 kilograms. So they're kind of needed as a placeholder, but they're not significant because they do nothing to show me the precision of my instrument. So my rule of thumb is just always go left to right and find your first non-zero and start counting from there. So ignore all the zeros to the left Now I'm here, and we can start saying that there's 5 sig figs. Ignore everything to the left. Now I'm at 9, so ignore all these. Once I'm at 9, I start counting, and I get 1 sig fig. Now, it's the zeros to the right that we really have to distinguish between. In this rule, I have 2 zeros to the right of non-zeros, so those are going to be significant. And 85.00 has 4 sig figs. There's 4 digits. They're all significant. 9.00000000 has 10 sig figs because I found that first non-zero and I just counted to the right. And I've counted 10 digits. So that has 10 sig figs. On the other hand, notice if there's not a decimal involved, then I only have 1 sig fig here. I stop counting the zeros. This could be ambiguous though, because what if I wanted to have 2 sig figs? And I know the 2 and the 0 for sure, but I don't know the other 2 zeros. I might have 3 sig figs. So that's really ambiguous. So how we can show that it has 4 sig figs is by adding a decimal. So if I add a decimal there, then I can count all 4 as sig figs. If I don't have a decimal there, these 3 zeros are all just placeholders. And 2000 technically only has 1 sig fig. The way I think of it, if I have a bank account, and I know that I have $2,000 to the penny, like I received $2,000 exactly, and I know to the penny I have $2,000. That's going to have 6 sig figs, or if I could write it like this. That has 4 sig figs if I put a decimal there. However, on the other hand, maybe I have like $1,937. Maybe I have $2,108. There's somewhere around 2,000 in there. I don't know the exact amount. In that case, I'm estimating. So only the 2 is significant. I know it's in that realm of 2,000, but because I'm estimating, now I only have 1 sig fig. So if I know it exactly, I have 4 sig figs. If I'm estimating, I only have 1. Now I might know that I have, I know I don't have 2,100, and I know I don't have 1,900. I have like maybe 2,030 or something like that, but I'm not sure if the 3 is there. So I know it's in the 2,000 something. I just don't know the other 2 numbers. I can gauge how certain I am based on, I can put a little hash mark above this number, and that tells me I know the first number is 2. I'm estimating the second number is 0, but I have no idea what the third and fourth number are. Or I could put it above this one, and that tells me I'm certain about the 2, I'm certain about the 0. Estimating that third 0, I have no idea what the fourth number is. So does that make sense how we can have different numbers of sig figs for the same value? That's where it gets complicated. But I want to look at some examples to see if we're catching on here. You can just say it or hold up your fingers if you know it. But I'm hoping we all get the first one. How many sig figs does 28.6 have? Yeah, I agree that would be 3. How about 3,440 with a decimal point?
Would it also be 3?
So, it'd be 4 because I put that decimal in there. That's telling me that zeros to the right of non-zeros are significant now. So it'd be 1, 2, 3, 4. If I didn't have that decimal there, then you'd be right. It'd be 3. So looking at C, does that help you? What would we say first?
3 would be, unless there's a decimal point there that I can't see.
There is no decimal point.
What Would it be 2?
Because there's no decimal point, it'd be 2. Because the decimal point would make it 3. Does that make sense? If I put a decimal point there, it becomes 3. But because there's no decimal, it's only 2. How about this one with D? Any guesses on? It has 4. Because I'm going to ignore the placeholders to the left, start at the first non-zero, and then count 1, 2, 3, 4. How about E? Do I count those zeros in E?
There'd be 5.
Yeah, there'd be 5. Some people were tempted to count these two, but we don't count those. Those are placeholders. I always start at the first non-zero. Some people get confused in how I explain it because I say zeros to the right. What I mean is zeros to the right of the non-zero are significant. Not every 0 to the right of the decimal. So 0067000, that has 5 because all 3 of those zeros counted. So you can see how the rules with zeros get a little tricky sometimes. So let's see if we can get this one. Which one would contain 3 Sig Figs? So I think that we're going to talk about rounding. I think we've done this since like elementary school, so most of this should be common sense at this point. But I'll go through the rules. If it's greater than 5, we're going to increase the number by 1. So 42.68 becomes 42.7. If it's less than 5, I'm going to keep it the same. So 17.32 becomes 17.3. If it's a 5, and it's followed by non-zeros, we're going to increase it by 1. So 2.785 becomes 2.79. If it's a 5 that doesn't have non-zeros after it, so like 4.635, that's going to become 4.64, just like it normally would. There is one strange rule for rounding with Sig Figs that it's kind of playing a 50-50 odds game, because if we have a 5 there, we don't know if it's supposed to be rounded up or if it's supposed to be rounded down because it's right in the middle. So technically, when you have an even number, so like something like 78.65, you're supposed to leave it 78.6. I'm not as picky about that rule. If you just want to kind of round up from 5, whenever you have a 5, I'm okay with that. But any questions about the rounding stuff? You good with that? So looking at 0.0255, if I round that to 2 Sig Figs, I'll let you think about that. So the last thing we're going to talk about today is adding and subtracting. So we're adding and subtracting. This is wordy. It's kind of confusing. I think when I show you with the math, it's going to make more sense. But when adding or subtracting, the answer has to have the same number of digits to the right of the decimal point as there are in the measurement having the fewest digits to the right of the decimal point. So you have to look at the number with less digits to the right of the decimal, and that's how many digits your answer should have. It's going to make more sense when we see it. And then we'll look at multiplication and division tomorrow, but in multiplication and division, I say it's kind of like the weakest link. The one that has the least sig figs is what your answer should have. So if you've got a number with 2 and a number with 4, your answer should only have 2 sig figs. So my calculations, I'm going to assume I meant to put a plus here. Might have actually meant to be a times. I don't know. Actually, yeah, let's make that a times. Because plus and minus are the same, but times has a little bit of a different rule. So if I have 5.44 minus 2.6103, the thing is, I only know this 2 digits here. I have no idea what this is, and I know in math class you'd make that a 0, but in reality, my measurement with sig figs, I don't know what either of those 2 numbers are. So if I have something I don't know minus a 3, that ends up being, I don't know. If I have x minus 0, it's still x. I don't know what that is. But then I can do the rest of the math. 4 minus 1 is 3. Borrow the 1 from there, and I get 14 minus 6 is 8. 4 minus 2 is 2. So my answer is 2.83 meters. And if I put that in my calculator, I would know just based on the fact that 5.44 has 2 digits after the decimal. So my answer, 2.83, can only have 2 digits after the decimal. Does that make a little more sense than what the wordy rule said? The other one, 2.4 times 15.82, I'm going to write it like this. I guess I'm just going to put this one in the calculator and tell you the rule. So 2.4 times 15.82. It's 37.968. But I don't want to use that whole big number. I only have 2 sig figs in one of the numbers. So this one has 2 sig figs. This one has 4 sig figs. Like I said, go with the weakest link. We're going to round this up to 38. And then because it's milliliters, those are going to cancel out, and we get 38 grams. Notice in this case I didn't care about the decimal. In multiplication and division, I don't care about the decimal. I just care about the number of sig figs in the total value. And honestly, most of our things in chemistry will involve the bottom part, where we just care about how many sig figs are in the number. Go with your lowest sig figs, and that's what your answer should be. A lot of times on tests and quizzes, they'll have the same number. So if both numbers have 3 sig figs, go with your answer should be in 3 sig figs. Any conversions or numbers on the conversion table, they don't have, their sig figs don't count. Only go with the numbers in the problem when you're determining how many sig figs to use. So that's where we're going to end up today. We're going to pick that up in the next lesson some more and practice with it.